When we map an algebraic equation onto a Cartesian plane, we are translating abstract math into a physical, geometric shape. But we can also work in reverse. If we are presented with an unknown graph, we need a way to determine if that shape actually represents a polynomial function. Our baseline for this comes from the simplest equations, linear and quadratic functions. When you plot a straight line or a simple parabola on graph paper, the physical act of drawing them requires no sudden stops or abrupt changes in direction. Because these foundational polynomials share these predictable geometric behaviors, we can look for those exact same visual rules in much more complex equations. The first constraint that governs every polynomial, regardless of its degree, is absolute smoothness. In geometric terms, this means the curve must flow effortlessly. It cannot have any sharp corners, jagged edges, or sudden snaps in trajectory. Every peak and valley is perfectly rounded. The second constraint is absolute continuity. You must be able to trace the entire function across the graph paper without ever lifting your pen from the page. Functions that lack these properties contain physical, topological defects. Any graph claiming to be a polynomial has to pass a strict visual inspection for both smoothness and continuity. Failing even one of these conditions means it is an impostor. It is highly efficient to diagnose these graphs by disqualification. Proving a graph is not a polynomial only requires finding a single defect. This graph shows a continuous curve that travels smoothly for a time, but then forms a distinct V-shaped point. If we subject this to the continuity test by tracing the path from left to right, the line remains unbroken. The tracing point navigates the entire shape without leaving the paper, so it passes the continuity constraint. But when we apply the smoothness test and examine the transitions, the tracing point hits the corner and halts. That single coordinate represents an abrupt jerk. The direction of the line snaps instantly, violating the rule of effortless transition. Despite being perfectly continuous, the presence of that single sharp corner mathematically proves this cannot be a polynomial function. The next subject in our lineup reveals a different type of structural failure. This graph is composed of curved segments, separated by a distinct, unbridgeable gap in the middle of the plane. Look at the individual segments in isolation. They are perfectly rounded and pass the smoothness test. The failure occurs during the continuity test. As we trace the path, we hit the empty space and run out of line. To reach the next coordinate and continue graphing, you are forced to lift your pen completely off the paper and drop it down at a new starting point. That physical jump defeats the absolute requirement of continuity. No matter how smooth the individual pieces are, a single gap definitively proves the function is not a polynomial. With the disqualifiers established, we can verify true polynomial functions. This graph shows a simple, straight diagonal line. It contains 0 corners and extends without any breaks. It easily passes both tests, verifying it as a valid linear polynomial function. Now consider this complex graph. It is an undulating curve featuring multiple distinct peaks and valleys. The transitions between the highs and lows are effortless, sweeping curves, and the path remains completely unbroken from left to right. These continuous, smooth variations in trajectory are not defects. They are the defining visual signatures of higher-degree polynomial functions. A valid polynomial graph is always an unbroken, continuous journey composed entirely of smooth transitions. Training your eye to spot topological anomalies, specifically sharp corners and empty gaps, is the fastest method to filter out the impostors. Once a graph passes these visual tests and is confirmed as a polynomial, we can extract specific algebraic data from its shape. Looking at this verified curve, the most crucial locations are the exact coordinates where the line crosses the horizontal axis of the graph paper. These intersections dictate the function's core geometry. In algebra, we call these crossing points the zeros of the function. Identifying them is the primary target for all future analysis of polynomials.